So I'd like to introduce Efthymia Tsamoura she's a research fellow at the Alan Turing Institute. She did her postdoc at the University of Oxford, and her main research area is databases.
Hello, thank you very much for the invitation. My name is Effie. I'm a research fellow of the Alan Turing Institute. I'm a computer scientist, and I'm doing research in databases and knowledge representation. So today I will present a recent work of mine, which is about how to query data under access patterns and integrity constraints. At this point, I would like to say that my area of expertise is quite different from the area of expertise of the two previous speakers. I'm not a statistician, so please feel free to interrupt me during the talk and ask me if something, whatever you think that it is unclear. I will start by providing the problem definition. What is the problem? The problem is given a conjunctive query over a schema with access restrictions and integrity constraints, and also given a user cost function, the goal is to find a plan that respects the access restrictions and is consistent with the constraints. And that plan should be optimal, should be minimum, or should have the minimum or maximum cost, depending on the user cost function. What are the access restrictions? The informal definition is that access restrictions are functions which require certain inputs and return all the records in the database that match these inputs. Now, what are the integrity constraints? The integrity constraints that we consider are given by tuple-generating dependencies, and we can also deal with equality-generating dependencies. These are first-order formulae. Don't worry about the notation. I hopefully will make things clear through the example. Suppose that we have a database over 5 relations. The relations are customer, which holds customer identifiers. We have the relation customer details, which holds further information about customers. We have a relation called products, and we also have the relations item and bought, which relate items to product identifiers and customers to the items that they have bought. Suppose also that we have these access methods, which simply say that the first two of them say that you can freely pull out all the records of customers and products without specifying any input. Now, the second two access interfaces work differently. In particular, this access interface says that in order to access items in the both relation, you should provide in the input a customer identifier, and what you will get in the output are all the records, are all the items that relate to this customer. The next access interface works similarly to the previous one and says that users should provide in the input a product identifier, and will get in the output all the items that relate to this product. Now our database has also these two constraints, and these two constraints simply say that both the customer and the customer details relations hold the same customer identifiers. Now, under these access methods, we can understand that the user query cannot be naively thrown to a database management system and executed. And this is simply because we don't have access to the customer details relation. However, the user query is answerable, and the user query becomes answerable if we take into account the following information. First, that there is the relation customer, which has an input-free access method, and second, that there are these two first-order formulae, these two dependencies, which say that all the customers identifiers that I need can be also found in the customer relation. In this slide, I summarize 3 of the many possible plans that can answer the user query, and these plans, the first one of these plans works as follows. First, we perform an input-free access to the customer relation. We pull out all the customer records, and for each customer identifier, we access the bought relation. Then we perform an input-free access to the product relation. Then for each returned product identifier, we access that item relation. At the very end, we join all the acquired tuples together. The second plan is similar to the first one in the sense that it's similar, but we just change the order where we access the relation. Finally, the third plan is an example of a pussy plan, what we call databases pussy plan. And these plans are particularly attractive in the database setting because they give to people, to database management systems, further opportunities for parallelization. So we could potentially parallelize the execution of this plan and this plan. Now, what are the applications of this problem? This problem finds applications in many different areas. Some of which are data integration, answering queries over web services, and answering queries over security-protected databases. What is data integration? Data integration is the problem where we have many heterogeneous databases with heterogeneous schemata, and we want to provide a global schema to the user that will represent the data of the remote schemata in a nice way, and we will also give the ability to user, instead of querying the different heterogeneous data, to query the global schema. What is answering queries over web services? This problem is how to answer queries in a setting where I have restrictive access over the data. Now let's see an example of a second example of this problem from the area of data integration and answering queries over web services. So suppose that the user wants to find publications that relate to pathways that appear in diseases. I don't know what the pathway is, so I just got this query from a biologist. Now, in order to answer this query, the biologist has to access data from these two databases. The first one is PMC Center, which provides information about publications. And the second database is Reactom, which provides information about pathways. Now, in order to access publications, PMC Central provides this web service, which accepts in the input a query written over any combination of these attributes and returns all the publications that match the input condition. In order to access pathways from Reactom, Reactom provides two web services, these two, where the first one accepts in the input an organism and returns a pathway, all the pathways that match this organism, and also provides this second web service which accepts in the input a pathway identifier and returns information about the corresponding pathway. Now, under these access interfaces, the user query, this query, cannot be naively executed, and cannot be naively executed simply because we don't have all the required inputs in order to call the web services. However, the user query is answerable. The user query is answerable if we take into account this constraint that says all the organisms of the pathway relation are also in the species relation, and that there is an input-free access method to the species relation. Under this extra information, if we rewrite our query to this query, then we can answer the user query as follows. First, we call this web service in order to pull out all the species from the database. Then for each returned organism, we access the pathways relation through this web service. And at the end, for each returned tuple, we also access this web service by providing in the input the organism. Before presenting our solution to this problem, I would like to say a few things about related work. So these two problems of how to answer queries under access restrictions and integrity constraints have been studied in the past, but they have been studied in isolation. For example, the solutions that have been proposed were able to deal with problems where there are web services that limit the way we access data, or the solutions that they were proposed they were applied in the setting, in data integration settings, but where the heterogeneous databases provide free access to the databases. Of course, there has been also some theoretical work that studied this problem, that jointly studied these two problems, one of which is my work. What is the contribution? The work that I will present you now proposes algorithms to jointly address these two problems, and also proposes variations of algorithms that produce both sequential and busy plans that can be parallelized. Another contribution of this work is that we extensively experimented with these algorithms, both in real world and synthetic scenarios. Now we'll present some key ideas of our work. At first, we had to come up with a plan language. What is our plan language? Our plan language incorporates access operators, which are parameterized by a relation and the access method that we will use in order to access the relation. And our plan language also incorporates dependent join operators, which extend traditional join operators by also specifying the inputs that should be provided from the left-hand side plan to the right-hand side plan in order to start its execution. Our plan language also incorporates the traditional select project join operators from relational algebra. I will not give any further details. I know that these things may sound cryptic to you. Each plan is also associated with the inputs that are required in order to execute the plan, and with implicit information. What the implicit information is? The implicit information is the information that is found through reasoning. What is our goal? Our goal is to find plans that are runnable standalone. These plans are called closed in our language, and are equivalent to our input query. These plans are called successful in our plan language. Now I'm afraid I don't have enough time to give the formal definition of what implicit information is. I will just say that implicit information is information that we are already aware of, but we don't know that we are aware of this information until we reason. Let me give you a very small example. So in this example, if we access the pathways relation, we know that we have also information, at least the organisms of the species relation. But until we reason, we don't know that we are aware of this information. Implicit information in our world, in our setting, is symbolically represented through facts. And the implicit information consists of three types of facts. The first one is facts of the hidden database. And what is the hidden database? The hidden database represents all the information that is currently stored in our database. How the hidden database is computed? The hidden database is computed after grounding the input query and then reasoning with the constraints. What grounding a query means? Grounding a query means that we simply substitute its variables with non-schema constants. The second type of information that is included in implicit information is consequences of facts exposed via reasoning. This may sound cryptic. Don't worry, we will see an example later. What is the third type of information? The third type of information is accessible values. What are accessible values? Accessible values are data that we got after doing explicit accesses. So in this slide, I summarize 4 plans, and for each plan I show their inputs and their implicit information. The first 3 plans are single access plans, where the third one is a plan that is a joint plan that it is composed out of these first 3 plans. The first thing that it should be noted is that in this plan we have implicit information regarding customer and customer details. How this came up? This came up via reasoning with this constraint, with this first order formula. The second thing that it must be noted is that the implicit information is computed compositionally, and in particular, the implicit information of this plan is a superset of the union of the implicit information of the corresponding plans. For completeness, in this slide, I show a plan that is successful and closed, which means that a plan that we can give to a database management system and can be executed. Putting all this information together, we can come up with a basic search algorithm, and the basic search algorithm works as follows. First, we create all single access plans, and then at each step, we create new plans by composing the plans that were found during the previous iterations of the algorithm. Now, after we create a new plan, we do what? We reason in order to find its implicit information, and then we estimate its cost. If the new plan has worse cost than the best plan found so far, then we simply discard it. Otherwise, we check if it is successful, if it is equivalent to the input query, and if it is equivalent, we update the best plan found so far. Now, at this point, I should say that in this work, we reason using the chase proof system. However, many other reasoning systems can be applied. For example, we could use some theorem provers like the theorem prover in order to do the reasoning. So far, so good. The previous algorithm is guaranteed to return the best plan if actually there is a plan that can answer our query. However, what is the problem of the previous algorithm? The problem of the previous algorithm is that it is inefficient. And in order to improve its performance, we employed several techniques, one of which is borrowed from traditional dynamic programming. Dynamic programming is a technique that it is applied in databases in order to find solutions by composing some optimal solutions found during previous steps. So what researchers do in dynamic programming, they group plans based on their atoms, based on the relations that they are going to access, and based optionally on the ordering of outputs. And then for each class, they keep the plan with a minimum cost. What is our approach? Our approach is similar to what it is done in dynamic programming, and it works as follows. The plans are grouped based on their inputs and on their implicit information, and then for each such group of plans, we discard the plans with the same or less implicit information and with the highest cost. What is the other optimization that we did? The other optimizations that we did are, first, in this step, we search the plan space in parallel. And the second optimization is that we reuse as much reasoning results as possible. In this slide, I'm trying to give an example of this idea. Suppose that we have these four plans which are grouped based on their implicit information into two groups. We know that if we form a plan by composing plans 1 and 3, then the implicit information of this new plan will be the same with the implicit information that would be created by composing plans 1 with 4, or by composing plans 2 and 3 or 2 and 4. I will not bother you with any other details about the algorithm. I will just say that we run experiments in order to assess the performance of our techniques, and we run experiments using real-world databases from the European Bioinformatics Institute. Why we chose these databases? We chose these databases simply because all of them provide access to their data through web services. That most of them required many inputs by the user. We also created a benchmark of queries of different sizes, queries that access 2, 3, 4, or 5 relations. And what we did is we compared the performance of our plan with the performance of randomly created plans. Now someone will ask why randomly created plans. I will say randomly created plans simply because there is no competitor that does what we do. So in this slide, I show some results. The horizontal axis corresponds to a query from our datasets, and the vertical axis corresponds to time. Okay. The blue bars correspond to the time that is required by a randomly created plan in order to return the full result set, while the green bars correspond to the time that is required by a plan outputted by our algorithm in order to return the full result set. What we can see is that we can see performance improvements of several orders of magnitude. This is my last slide, and in the last slide, I will say that in general, I'm looking for people to collaborate with in order to extend this work and to deal with more access interfaces and to deal with settings where we have unpredictable access latencies, or we have resources where we don't have any metadata, like resources where we are not allowed we don't have any information about the size of the remote data set. I recently received a funding from Intel in order to continue my research and to work on this problem and find application of these problems in different settings, like access data under privacy restrictions. And I'm looking for collaborators to work on this idea. So if you are interested, please come and find me. My office is the first one in this side, and also 357 in the computer science department in Oxford University. Thank you very much.
So again, we have 5 minutes for questions. So does anybody have a question?
You can ask anything, I don't know.
Okay, so...
okay, we have some.
So I guess actually when you had your results slide,
Yeah. Sure, yeah.
So I don't know maybe the way this is presented, but in some
Yeah.
ways, the thing I took away most about that is on many cases, your performance and the random performance is quite similar. Now there are certainly some examples where your performance is much better, and a lot better than say 7 and 8 there. Can you say anything about what kinds of characteristics of the problems meant that some were sped up and others were disappointing, shall we say?
Thank you very much, because this is something that I wanted to mention, but I forgot to say this. So in these cases, we have the same performance because there is actually a single plan that answers the query. There is only one plan that can answer the query. And there is only one plan because due to the access restrictions, there are not many possibilities to first access this or that. Due to the access restrictions, we are restricted to access first relation 1, then relation 2, then relation 3, then relation 4. So in these cases, we do the same with the random plan because we cannot do better. But thanks for this is something that I had in mind to mention. I forgot it.
My question is
Yeah.
about the integrity constraints. So
What?
Integrity constraints.
Integrity constraints, yeah.
So basically, it's like, let's say I have many relations, and some relations have composite keys.
Yes, yeah, we can handle, the integrity. Let's go to the first slide, please. So we can handle both tuple-generating dependencies. An example of tuple-generating dependencies are inclusion dependencies, but we can also handle EGDs. EGDs represent keys in your setting. Okay, sure, I forgot to add this because I didn't want to put much notation. In general, my presentation was quite high level. I didn't want to bother you with many details with logic because there is a strong logic background in this work. But I was pretty sure that you are not from this background. That's why I skipped all the nasty details.
Okay, just a question.
Yeah, sure.
It's like, so let's say I have a relation that is not normalized.
A relation that?
That is unnormalized, which means that the table that is not in first normal form, second normal form, third normal form, is a flat table. So
Yeah.
Can you actually say a bit more about your method of these kinds of tables?
we don't care about the normalization of the tables, meaning that we don't care if our data is in first normal form, in second normal form, or in third normal form. All these dependencies can be represented, are encapsulated by this formula. And as long as our dependencies are encapsulated by this formula, it's absolutely fine if the database administrator has normalized or not the schema. Yeah.
Perhaps a very naive question, because this is very far from, almost orthogonal to what I have had in my life.
Yes, sure.
So I have been looking at probabilistic databases lately with some excitement because of how quickly they give you something back.
Sure.
I wonder, are these results exact in the sense that you get all the records that are available in the database that satisfy these constraints? And
Yeah, sure.
would you achieve
Sure.
performance gains if you
Yes.
simply have the probability threshold that a record to be returned if it's the probability of satisfying these constraints is higher than the specified threshold? If that makes sense.
You brought to the table many different issues that may somehow may not relate. You brought to the issue of probabilistic databases.
Yeah.
Then you said about result completeness.
Okay.
And then you mentioned about trying to probabilistically satisfy these constraints.
What I mean is that other results you're getting is exact. So you retrieve all the records that satisfy a particular constraint exactly.
We return all the records that satisfy the user query and are consistent with the constraints. Of course, the data is always consistent to the constraints. So the question is if you will able 1 minute, so I have to reply fast. we can continue this discussion offline. Just for completeness, I will say this: the data satisfy the constraints. So the problem is you will be able to access the data to access the data in order to answer your query. First, second, if you also brought the issue of reasoning under uncertainty. This is another research area, how to reason with uncertainty. And there is also the issue of completeness. Yes, we are complete in the sense that we will get all data that satisfy the user query. Of course, this is the fast answer because it is the 1 minute answer. The long answer will be, we can discuss the semantics of the plants of the fly. So there are different semantics. There are certain answer semantics, which are mostly made in the ontology setting, and there are the closed word semantics. We can discuss this later anytime you like.
I want to thank Efthymia Tsamoura.